And now I'd like to introduce the director of the Geophysical Institute, Bob McCoy, to welcome our speaker.
Like Fritz, I'd like to thank you all for coming out tonight and braving the elements. We're in for a real treat. It's my pleasure to introduce tonight's speaker, Professor Mark Conde. He talks a little funny because he's from Australia, but he probably thinks all of us talk a little funny, so this is fair game. Mark is from Tasmania, I believe, in Australia. He got his PhD from the University of Adelaide. And he did his research is based on lots of field work studying the Aurora over Antarctica. After graduating, he worked as a computer programmer for the Australian Antarctic Division Marine Science Program, and later as a postdoc at La Trobe University. In 1993, he came to Alaska to work on an upgrade and revitalization program for the Poker Flat Research Range. If I could give that a plug, March 9th is the 50th anniversary of the Poker Flat Research Range. We're having a celebration out at the range from about 8 to midnight, so please come out. I think there's buses. You can ask Fritz later about some of the details, but 50 years is a long time. It's the only university-owned rocket range, the biggest rocket range in the world, and it's 50 years old this March. Getting back to Mark, in 2002, he accepted a joint academic appointment at University of Alaska in the College of Natural Science and Mathematics, and also in the Geophysical Institute. He is a professor of physics, and he's a space physicist in the Geophysical Institute. His experimental work focuses on weather in the Earth's upper atmosphere, where he studies the ionosphere and upper atmosphere over Alaska, Antarctica, Norway, and Sweden. He makes exquisite measurements of air glow and wind in the upper atmosphere, and he's a rocket scientist. So with that, I'd like to welcome Mark.
Well, thank you, Bob. Let me see if I can get this presentation going here. Excellent. All right, well, I'd like to add my voice to the thanks for everyone to come out here. I feel I've been a little bit one-upped because I want to talk about weather in space and trust Alaska to throw some weather at us and some weather you can actually touch and feel and see, and to one-up my story a little bit. But that's why we're here in Alaska, because we like that sort of thing. So what I want to do tonight, I want to tell you a story about weather in space, starting with a rather grumpy middle-aged star called the Sun, which has a habit of throwing tantrums every so often and throwing stuff at the kids, including us. And when that stuff hits our magnetic field, it creates disturbances in the magnetic field. Particles rain down on the top of the atmosphere, produce the aurora, and in that process it disturbs the atmosphere itself and drives changes in wind, changes in temperature, things that we would think of as weather. And it's not just an academic interest, it affects spacecraft, it affects orbits, it affects communication, and so it's something that the United States and technologically advanced countries care a lot about. Furthermore, because the aurora is an integral part of that story, and the aurora occurs over Alaska, hopefully by the end of tonight you can go out, maybe not tonight, but you can go out when the sky is clear and look up at the aurora and see some of the phenomena that I'm talking about happening just with your eyes above you here in Fairbanks, Alaska. So this is my opening slide, and the reason that I've put this up is because, as I said, this weather that occurs at the top layer of the atmosphere, which I'll talk about in a minute, affects spacecraft orbits. And one of the things I'm going to show you is that it's very difficult to predict when a spacecraft will actually re-enter the Earth's atmosphere. As the orbit decays, eventually it comes down. And that's a really hard prediction to make. And one of the reasons it's hard to make that prediction is because the weather that disturbs the atmosphere is unpredictable. And so this is a picture, just an artist's impression of a spacecraft re-entering the atmosphere, and when and where that happens is very heavily dependent on the story that I'm going to tell, hopefully, here tonight. So I want to give you an outline of where I'm headed with this talk. So I want to start off by talking about what part of the atmosphere I'm going to be talking about. I want to tell you a little bit about what it's like up there. It's rather different to what it is down here on the ground. I want to tell you why weather occurs at these sorts of altitudes. I want to tell you why there's weather, including storms, big disturbances to the atmosphere. I want to tell you what these storms do when they're in progress, what they look like. I want to tell you how we study them, why we care about them, and I want to finish up with saying a little bit about what we can do about them. The answer to that is that we can't actually do much to stop them, but we might at least be able to be warned and understand them. All right, so to start at the beginning, I want to talk about the region of the atmosphere that I'm talking about here, or I'm going to be discussing. And the atmosphere sort of gradually fades away with height. As you go up, it gets thinner and thinner, the pressure drops, the density drops, and there isn't really, my title was weather at the top, storms at the top of the atmosphere. There isn't really a defined top of the atmosphere, it just fades away. But the last sort of wisp of atmosphere that behaves like what we would think of as a gas is in this region from, you probably can't read this, from 100 kilometres or 90 kilometres to 100 kilometres and up. I've vaguely coloured that yellow, I don't know if you can see it, up to 400 or 500 kilometres. So 100 kilometres is about 62 miles. I'll apologise for using metric units a bit. That's what we tend to use in science, but 62 miles and up, something like that, is the area that I'll be talking about. Let's see, there's lots of, as I said, the pressure and density drops in the atmosphere as you go up. It just gets more and more tenuous. So by the time you're up to here, the pressure is, the pressure on the ground is about 1,000 millibars. By the time you're up here, it's 1/10,000,000th of a millibar. So it's very, very tenuous. Another thing that helps you think about what's going on here is this quantity which scientists call the mean free path. And that is, if you are an atom or a molecule of the air, you collide into other atoms and molecules frequently. In the room here, when an atom or a molecule collides with another one, it gets to go, I think, a few tens of nanometers. So maybe a thousandth of a micron, something like that. No, sorry, a tenth or a hundredth of a micron, a very short distance before it will collide with another one. By the time you go up to 500 kilometres altitude, the air molecules can travel 100 kilometres between collisions. So that tells you that the gas can't really communicate amongst itself very much because they're not colliding, the molecules are not colliding into each other very much. That's not to say they're rare, there's still an awful lot of them. As you'll see, there's trillions per cubic metre, but they're so small they don't collide much. When you get to the top of this region, you enter what's called the spray region. And I don't know if people have seen state lottery machines and things where they have a whole bunch of balls in a big chamber and they blow air in them and all the balls bounce around, and up at the top you see little balls bouncing along the surface. That's pretty much what happens at the top of the atmosphere. The very last of these particles, they experience a collision and they just sort of go up on a ballistic trajectory and come down again. And so they follow these sort of parabolic trajectories there. And so it's called the spray region because it's like they're being sprayed up and dropping down again. So very different, and lots of other properties that I won't discuss, but all the properties are completely different up here. One other thing I'll comment is that the chemical species separate out according to their weight up here. But very surprisingly, this curve here is the temperature, and there's a big increase in temperature. So down here on the ground, it gets cooler with altitude until you get to the top of what's called the troposphere. It then warms up in the stratosphere because of ozone, continues cooling again once you get past the ozone, but here it gets very hot. The reason for that is ultraviolet light from the sun heats the top of the atmosphere, and because it's so hot, more than 1,000 kelvins at the very top of the atmosphere, we call this the thermosphere, thermo being heat. All right, next question is, everybody knows from watching science fiction movies or something, if you open the door of the airlock, all the gas escapes and disappears. Well, here's the top of the atmosphere, here's empty space, it's a vacuum. Why doesn't Earth's atmosphere just all escape off into space? Fair question. The answer is actually pretty simple, and the answer is our atmosphere is held and trapped around our planet by gravity. And the way to think about it, I talked about that spray region. I said these things head up in big parabolic ballistic arcs. You can ask, how fast does an air molecule have to go in order to be able to escape and get out into space? Turns out it has to be going at about 11 kilometres per second. That's pretty fast. That'll get you across Alaska. What's Alaska? 1,000. It'll get you across Alaska in 100 seconds. The atmosphere just isn't hot enough for the gas to be moving that fast. So sure, these things they can bounce up, but they always fall back down again. There's not enough energy for them to escape and get away from our gravity. And the way scientists think about this, they think, well, occasionally one of them actually does manage to get away. And if you total it all up, how long would it take, at the rate that the very occasional ones do manage to escape, how long would it take for Earth to lose its atmosphere? The answer is tens or hundreds of billions of years. So our atmosphere is not going anywhere, certainly not in our lifetime, and probably not in the lifetime of the solar system. It's very stable. However, that's for most of it. There are actually just little hydrogen atoms up there. Hydrogen is so light that hydrogen actually is lost easily, and the only reason that you can find any hydrogen up there is that it's constantly replaced from oceans below. That's by the way. All right, so I talked about storms at the edge of space. What do I mean by the edge of space? I looked around for some definitions. I found that the Red Bull company that makes soda, they had an idea of what they meant by the edge of space, and I got a little clip from one of their promos here, if I can drive my cursor around. And if it'll play.
A mission to the edge of space. Felix, an Austrian base jumper, is aiming to break the world freefall record by jumping from 120,000 feet above the Earth's surface.
How about that, buddy? How about that?
So according to Red Bull, the edge of space is at 128,000 feet or 40 kilometres. That's in the stratosphere. The atmosphere still looks very atmospheric at that height. So I don't much like that definition for the edge of space. If you look around for what people would call where space begins, a very common definition is this thing called the Kármán line. And it was invented by an aeronautical engineer, and he said, well, the air gets gets more and more tenuous as you go up, less and less thick. It gets harder and harder for an aircraft to fly because there's less air to support it. So the only way an aircraft can remain flying is to go faster and faster as you go up. And eventually, when you get to about 100 kilometres altitude, for a typical aircraft, the atmosphere has become so thin that the speed it would have to be going at would be faster than the escape speed faster than orbital speed around Earth, and so it would not remain close to Earth. It would escape, and so basically no form of conventional aerodynamic flight is possible above about 100 kilometres by that sort of thinking. All sorts of other things change at this altitude, 62 miles, so that's a pretty good definition of the start of space. You could also say, when does the atmosphere stop behaving like a fluid? When do collisions stop being important? That's around 500 kilometres. But there's really no hard edge, so I'm using a little bit of, what's the word? Being a little bit loose with language when I talk about the edge of space here. I don't know how much you can see of this, but this is another really good way to think about when you're in space, and that is, if I put a satellite up there, as the satellite flies, it experiences a little bit of drag moving through the atmosphere, and it gradually loses height and falls down. So the question is, how high do you have to be in order for your spacecraft to not fall down? And there's not one simple answer to that either, because really the answer is, how long do you want to stay up there? So this is a plot, mostly Soviet spacecraft debris. And on the x-axis of this plot, we have altitude. So I don't know if you can read it, but this is 250 kilometres here, this is 190 kilometres, and this is 300 kilometres. So basically 200 to 300 kilometres on this axis. And on this axis is the number of days that these things actually remained in orbit. So if you look at the main curve here, at 250 kilometres, things fell out of orbit in less than 5 days. Now, the length of time you stay in orbit depends a little bit on how dense you are. It depends how much drag you've got, so there's some variability here. But, if you want to be in orbit for years, you have to be well above 300 kilometres, probably more like 400 kilometres if you want something to stay up there for years and function as a long-term spacecraft. As spacecraft start to come down, they encounter thicker and thicker atmosphere as they come down, and their lifetime gets shorter and shorter and shorter until below about 200 kilometres, it's game over. You only get a few orbits after that, and then the spacecraft re-enters. So where can a spacecraft continue to orbit? I would say 350 kilometres and above is a good starting point. The space station flies 370, 380, and it has to be boosted periodically because it's losing height. All right, so what have we got? We've got a very tenuous atmosphere. Collisions are rare. Mean free path is really long. Is it even a gas? Does it make sense to talk about wind when the gas is so thin? Well, the answer is yes, at least up to 400 or 500 kilometres. And I can show that to you. Before I play this video, I'll tell you what it is. This is a view of the sky taken from Toolik Lake in Alaska, which is up north of the Brooks Range on the Hall Road up to Prudhoe Bay. And this video was taken during a rocket mission that we conducted in 2003 called HEX. And what you'll see a rocket pass. This is stars in the background, and this is Aurora, this sort of background here. You'll see a rocket pass across the field of view, and it's releasing clouds of gas that you can see as it goes through. Little puffs of gas. You'll see a bunch of little puffs, and you will see those puffs moving up the screen because they're moving with the wind. Now, this rocket's at 150 kilometres altitude. So there it is, it's passing across there. These are the gas clouds it releases, and we can see them moving across with respect to the stars. So those gas clouds are telling us what the wind is doing 150 kilometres up, which is, a spacecraft there wouldn't last long, but it's pretty much in space. There's a satellite passing through the field of view here as well. So yes, there's a gas there, and yes, there is wind. It behaves like wind, and it'll push things around just like the wind does, even though it's very tenuous. If I can move to the next slide. This is another just interesting thing. This is 2 rockets launched from Poker Flat shortly after each other. You're looking up from below. You can see the rocket heading up, and you can see a trail of gas released. I was going to try and stop this part way through because there's a very interesting point that this shows. If I stop it about there, what you can see is you can see all these billows and structure in the. This is a continuous trail of gas released by the rocket. You can see it's turbulent. Same sort of thing you experience in an aircraft. Turbulence here, but then eventually, somewhere a bit above 100 kilometres, everything goes smooth and clean and the turbulence stops. That's because the atmosphere is becoming so thin that the mean free path is bigger than the size of the turbulence, and the atmosphere just can't sustain the turbulence anymore. So above 100 and maybe 110 kilometres, there's no turbulence in the atmosphere anymore, unlike down on the ground here. All right, so there is wind, and we can see it by releasing a chemical. Why does it blow? What causes the wind to blow? Well, there's basically 2 things that drive the wind at these altitudes. One is the same thing that drives the wind down here on the ground, and that is a difference in pressure. The main reason you have winds at ground level is you've got high and low pressure systems in close proximity. When there's a pressure difference, that causes the wind to move. It plays out differently at these altitudes, though. This is meant to be this is obviously a view of the Earth. I'm imagining this is the daylit, sunlit side of the Earth, and this point here is directly beneath the sun. This is where the sun's directly overhead. The sun heats Earth's atmosphere on the day side, creates a high pressure, but unlike down on the ground, the wind blows around the high and low pressure systems. They circulate like vortices. The atmosphere is different up here. The wind just blows directly away from the high pressure, around the Earth and towards the low pressure on the night side. That's the basic solar-driven circulation of the atmosphere up here. We call it the solar diurnal tide. Now, on top of that, you can see these 2 vortices here, counter-rotating vortices. They are driven by essentially the same process that causes the aurora. And so the aurora is just one thing that you can see. If you imagine the atmosphere is like a big cathode ray tube. When particles hit it, you see where the particles are impacting the atmosphere, but that's just one signature of a whole structure that extends out into space. And what that does, associated with the aurora, there are electric fields that are created by the interaction of the solar wind and the Earth's magnetic field. A portion of the upper atmosphere is not neutral particles, not neutral atoms or molecules, but ions. They've had a charge removed, they're ions. They move as a result of these electric fields, and they move in these counter-rotating vortices like that. When these ions bump into the atmosphere that they're embedded in, they stir it up. It's just like a big stirring stick causing the atmosphere to circulate like this. And the whole story of this weather that occurs in the atmosphere is this. This is the thing that disturbs what would otherwise be a fairly simple day-to-night wind flow caused by the sun. This is quite dynamic. It changes in size, it changes in intensity, and changes the amount by which the atmosphere is stirred up. And that's what drives these things we're calling storms, is the changing input from the processes that cause aurora. And I can you don't have to believe me, I can actually show you this in a movie. So this is another complicated slide. I apologise for some of these slides being a bit complicated, but this is a picture of Alaska here. In the middle is a coloured circle. That is the region that is viewed by a camera at Poker Flat, an all-sky camera looking up into the sky. There's a couple of different colours here. There's green, yellow and red. The green is showing the brightness of the structures we're looking at, the aurora, or in this case twilight. The red and blue are showing temperature. We won't worry about that too much. In the background you can see these yellow arrows. These yellow arrows are measured by a network of radars across Alaska and around Alaska. These yellow arrows are showing where the ions are moving. They're essentially showing this pattern here caused by the ions. The white arrows are the wind. I'll tell you later how we measure the wind. And what you can see, even before I start this playing, you can see that the ions moving like this have imposed their will on the background atmosphere and caused the atmosphere to flow along with them. If these weren't doing that, the atmosphere would be flowing in the other direction, pushed by the sun. This is right around sunset. The wind would be blowing eastward, were it not for the motion of the ions. So I'm going to play this video and comment on a few things. So you can see the ions, changing. They're very dynamic. They change their flow. The ion motion has become weaker. The winds have become weaker. There's less ion motion pushing winds around at the moment. I've still got the sun down here affecting these, this portion. Now here's the aurora. The aurora is getting brighter. It's Fairbanks here. So the aurora is just moving south, heading over Fairbanks. These are more ion motions measured with a different instrument, a different radar. The aurora is now getting quite active. We've got quite strong wind blowing to the west. The ions are starting to get a bit confused in which direction they want to go, and shortly they'll change instead of blowing this way, they'll start to blow down here, and shortly afterwards you'll see the winds react to that. So the ions are starting to turn their motion here, and now you can see the winds responding. The ions have changed their mind about where they want to go, and the winds are picking, are following suit with some delay. It takes a while for the ions to stir up the winds. And towards the end of this video, you'll see the aurora get quite active, and you'll see the winds really pick up. So the aurora is starting to pick up here now. It should get even... This blue colour tells me the aurora is really quite energetic, and the winds are blowing now southward, and they're really quite strong. Look at them picking up here. This is all driven by the aurora moving the air around at the top of the atmosphere. I think that went back to the beginning, so I'll go on to the next slide. So the point of that was to try and convince you that motion of the ions associated with the aurora pushes the wind around. So the aurora and the ions pushes the wind around. Where does the aurora occur? Well, we all know from Fairbanks that you see aurora over Fairbanks, but we can only see a little piece of the aurora from here. We can't see the whole structure. If you go out into space and look down from well above the Earth, you can paint in the whole complete edifice that is the aurora at any given time. This particular image is actually not a single snapshot in time. This is taken by a spacecraft called Timed, and it was a low-orbiting spacecraft, and it actually took swaths. It would orbit across and see a swath of the Earth. And so what I've done here to make this image is I've built up, I think there's about 11 or 12 or 13 orbits here where we've merged them and stitched them together to produce a continuous view of the aurora. And what do you see? Well, you see that the aurora exists in an oval-shaped region like this. It's centred on the magnetic pole, which is here somewhere, and it passes pretty much smack bang over Alaska. This is why Alaska matters in this story, because Alaska is right where the action is for stirring up storms and wind at the top of our atmosphere. Again, another busy slide. I apologise for that, but I think the point is simple enough, and the purpose of this slide is to answer the question, why is Alaska, or what is it about this region that makes, why does the aurora occur here? Why doesn't it occur down here? Why doesn't it occur up there? Why this ring that looks like that? I'm attempting to answer that here. So, what is the aurora? The aurora are particles from space heading down the Earth's magnetic field until they hit the top of the atmosphere and causing the atmosphere to glow. So if you're going to have aurora, you need two things. You need a magnetic field to guide the particles down, and you need a source of particles to create the aurora. Now these particles only travel along these magnetic field lines. They don't tend to travel across the magnetic field lines. So if you're down here at mid-latitudes or low latitudes, the magnetic field lines that could provide you with some auroral particles, they just don't go very far out into space. They don't get far enough out to reach any sort of a reservoir of material that would supply the particles to produce the aurora. Conversely, if you go to really high latitudes, these field lines go well out into space. It turns out you've got to know where the particles are coming from. Where is the reservoir of material that feeds the aurora? And where it is, it's in this region here behind the Earth. The sun's here, the sun's blowing across here. So the sun's on the left of this picture. Behind the Earth is this big long structure called the plasma sheet. Material accumulates there. It's actually squeezed into a sheet in this region here by the magnetic field. And then if you follow these field lines down, they sort of produce two funnels or horns that come down and hit the Earth at those sort of high latitudes, but not at the poles and not at the equator, but in a ring that runs around here. These are the field lines that map out to the reservoir, to the place where you can get material to produce an aurora from. So that's why the aurora occurs over Alaska and in a ring that includes, the Arctic regions. The same thing happens in the Antarctic. There's a mirror image down here, or roughly mirror image down here. And that's why it matters to us. So, what have we got? We've got tides, we've got something that can disturb the winds. The question is, how blustery is this weather? Is it once in a while you get a storm, or is it always going all over the place? Well, the source of the material in that plasma sheet comes from a few different places, but the source of the activity, at least, is the sun. And here, this is a video. Actually, before I play the video, I'll tell you what you're looking at. You're looking at the sun taken from a spacecraft. The sun itself is this white circle here. This is a camera looking directly at the sun, an incredibly sensitive camera looking directly at the sun. If it looked directly at the sun, it would be at least blinded and probably destroyed by the bright light from the sun. So what they do is they put a metal disc in front of it, which is this dark thing here, and in a rather crude fashion, to keep the disc in place, there's a stick running down here. It's a disc on the end of a stick that's in the way of the sun. And they've sort of done it. They've tried to blur the stick out here, but you can still see that it's there. So the sun is behind this disc. This is rather a high-stakes instrument. If they get it wrong and it wanders around so that the sun peeps out from behind this thing, it would probably be game over. With the sun so bright, you block it. Now you can turn the sensitivity of your camera way up. You're above the atmosphere, so there's no light from the atmosphere. You're looking at the blackness of space. With that high gain, high sensitivity, now you can see streamers coming out from the sun. This is the atmosphere of the sun streaming away from the sun. But doesn't look like that. This is what it really looks like. What you're seeing here is an actual view of what we call the solar wind. This is material leaving the sun all the time, and punctuated in amongst that are these enormous explosions. There are things that occur on the surface of the sun called solar flares. When a flare goes off, it causes an eruption, and it just spits a big bunch of material into space. A large cloud that spreads out fills the solar system, pretty much, or half the solar system, one side. You can also see there's some persistent streamers coming out of here, things that are not that eruptive. They last for a while. Why are they there? Well, it turns out this atmosphere of the sun's a bit leaky. It gets big holes in it that are called coronal holes. So as well as the explosions, producing big clouds of material coming out eruptively, there are these sort of persistent holes in the atmosphere where material is leaking out all the time. The combination of these two things, either an explosive eruption or a stream, it's a bit like being downstream of a fire hose, a stream coming from the sun, either of those, when they hit the Earth, they cause a disturbance and produce bright aurora, all sorts of disruptions to power grids, communications, satellites, and the sorts of things we're talking about. I should mention, by the way, these storms affect a lot more than just the wind and temperature in the upper atmosphere. They affect a whole bunch of things, but I'm focusing on their effect on the atmosphere itself. So two reasons why we get, dramatic changes in levels of activity. One is because of an eruption, and one is we might get hit by one of these streams. That's these things here, these persistent streams coming out from the sun. All right, this is an animation, I think, produced by NASA, and what it's showing here, there's an eruption from the sun. Here's our poor little Earth here. You can see how big this front of material that is erupted from the sun is. When it hits the Earth, it disrupts our magnetic field. The magnetic field's got this comet shape. You can see a big wave passing down the magnetic field. The magnetic field becomes compressed. The electric and magnetic fields are perturbed. particles move around and ultimately rain down on the Earth. It's a little bit hard to see what's going on here, but the main point of this video is to just see that huge cloud of material, this shock front coming out from the sun, this enormous cloud of material that strikes the Earth. It takes about 2 to 3 days to get from the sun to the Earth to produce this disruption that we experience. So, when it gets here, what does it do? Well, this is a very famous sequence in our area of study. This was taken in the early 80s by one of our colleagues up in the Geophysical Institute, John Craven, and he was at the time working at the University of Iowa with other colleagues. This was taken by a spacecraft called Dynamics Explorer 2, and it was one of the first spacecraft to give a really good, large-scale picture of what the Aurora is doing. Here's a picture of what the Aurora looked like seen by this spacecraft, and then there's a sequence here. These are 12 minutes apart. You can see there's an auroral oval which is relatively quiet. There's a little bit of activity here, but it's not all that bright. Somewhere about here, things start to brighten up, and then all of a sudden the Aurora gets much brighter, fills in here. Activity is increased very dramatically. Now, this is not quite the same process as what I showed you before. This is actually what's called a substorm. This is the Aurora. This is the Earth's magnetic field and the plasma contained in it becoming unstable in and of itself and dumping a bunch of stuff down on Earth. So this particular event doesn't need a shock front from the sun, but it's the same general idea. The Aurora goes from being quiet to being very active in a short space of time and causing lots and lots of disruption. As I said, this particular one would have happened regardless of what the sun did because the whole system just became unstable. That happens commonly. If you go outside at night at 10, 11, 12 o'clock at night, sometimes you'll see an auroral arc that's sitting there and it'll move gradually south, and all of a sudden it'll brighten suddenly, and for half an hour the sky will be filled with what some of my colleagues called Hollywood aurora, super bright, colourful, fast-moving aurora. That's what that same thing looks like if you look down at the whole system from space. Let's see. All right, so the sun disrupts the upper atmosphere. What are the effects? Well, this is 2 days of measurements taken with our instruments. This is taken from McMurdo Station in Antarctica, and it's looking at an altitude of about 240 kilometres, and it's just plotting temperature as a function of time. Let's see, this is 700 kelvins, 800 kelvins, 900 kelvins. The atmosphere's sitting around 800 kelvins. That's about what you'd expect for this altitude. It's hot, but that's what you'd expect. Then all of a sudden it started heating up, and then it heated really dramatically at the end of this day. So dramatically it went off scale on this plot, and it stayed off scale. I've got no idea what it did up here. I could probably find out if I replotted it, but the routine things, it's off scale. And it wasn't for 18 hours later or something that it gradually started to recover and come down. This is a big increase in temperature. This is 400-500 kelvins heating lasting for more than a day. That really disrupts the atmosphere. It's changed the temperature by 50%. It's a big disruption, and in this case, lasted for a day or so. Oh, I'm doing more than I need to do here. Well, maybe maybe this was just a one-off thing, a special rare event. Not really. There's a lot on this slide. I just want to focus on the top panel here. This is data from 2012 fall to 2013 spring, so it's a whole winter season of measurements, again taken from Toolik Lake up north of the Brooks Range. It's showing temperature, and the black points here are the temperature that was measured by our instrument Toolik Lake. You can see a seasonal effect. It's, as we went into winter, it cooled down a bit. This is 800 kelvins here. It was maybe 900, 1,000 in fall and back again in spring. So a seasonal effect here. There's other bumps here caused by the sun rotates, and sometimes the sun's a little bit more active than the other times, and when those active parts of the sun pass in our field of view, it warms things up. So there's a bunch of ups and downs here caused by just the background effects of the sun. But look at these spikes here, and here, and here, and here, and here. These are the storms I'm talking about, and you can see how often they're occurring. They're occurring, once a month or something. Not predictably in time. Sometimes you'll get 2 or 3 of them in a month. Sometimes it'll go for a relatively long period without seeing them. But they are common events, and they're large disruptions in temperature, and as you'll see, large disruptions in wind. I'm making more work of this. I'm going to skip this slide. So we've talked about temperature. What about wind? Well, this is, again, a busy slide. I apologise for that. This is 4 days in March of 2013. You can barely see it, but there's wind arrows here and there's temperature in the background. This is a slightly active day, but this is a storm day. You can see, these are 2 quiet days that follow. This is what the wind looks like on a quiet day. You can see how disrupted the wind was on the day of this storm here. This is the vertical component of the wind, just the up and down, the atmosphere moving up and down. A few waves in the atmosphere are common here, but big oscillations during the storm and then much quieter again after the storm. So, winds, both horizontal winds blowing across Alaska and vertical winds and a few other things that I haven't got time to discuss, all disturbed on this storm day. So the storms happen, every month or so, and they're big. All right, what do the winds do? Well, I've got another video to show you here. What this is showing you is winds measured over Alaska with our instrumentation at about 250 kilometres altitude. That's up there, almost high enough to be where the spacecraft are, and if you know the winds here, you know what the winds are doing at the height of the spacecraft. You'll see all-sky camera views in the background. These arrows are showing the wind. And what I've done, each of these little coloured spots, this will become obvious in a minute. Imagine if you release a plume of smoke into this wind field, you could follow where that smoke goes and you can see what effect the wind would have on how things are carried around. It turns out when the aurora is active, it modifies the chemistry of the atmosphere. It changes the actual chemical composition of the atmosphere, and then the wind takes those modified air parcels and moves them somewhere. If you're downwind of us, you'll have different air passing over you than you would normally experience. So you'd like to know what the wind does to that modified air. So let's have a look. So you can see these smoke plumes being released into the wind field. This is done computationally by a computer. Wind blowing to the west is transporting things to the west. But now the aurora's picked up. And look at that, the wind turned around, and now these trails that the smoke plumes are producing have completely changed direction. Look at this tangled mess here. Imagine you're a forecaster and you're trying to predict where things are going to go, good luck with that. And you can just see how strong this flow has become in response to that aurora. Now, at least, it's relatively clean, but during that transition, when the storm is starting, the flow fields just become, there's a little bit of, this is what we saw earlier, the flow to the east here to the west, but this transition here produces incredibly complicated transport trajectories. You already knew this. Anyone who's mixed paint knows that stirring up a fluid mixes things up, but you don't sort of think of it as happening in the upper atmosphere. I'm making more work for this one. All right, I'm heading on to the why do we care about this part of the story. And this slide is, it might look a little dull here, but this really speaks to the heart of why the United States and other nations care about this and why they're willing to invest a lot of effort in it. What this is showing about a year of data, and if we just look at the top slide here, it's actually showing the density of the atmosphere at 400 kilometres. That's the density, that's pounds per cubic foot, if you like, or kilograms per cubic metre. It's the mass density of the atmosphere. And let's see, the blue curve are actual measurements from spacecraft. You can see these oscillations, that's caused by the sun rotating. You can see this sort of trend, that's a seasonal trend. But look at these big spikes here. The density of the atmosphere increased, and it increased a lot, doubled during this period here. What does that mean? I have a colleague at the University of New Hampshire who says that means that all the spacecraft hit a speed bump. All of a sudden, they're flying along through nice thin air, and wham, the density goes way up. They're just slowed down and retarded by this speed bump that's been produced as a result of a storm. That affects the orbit, that affects where they're going to go. I'm making this too hard. Let me do this. I'm going to skip this slide because there's too much on it. Here's the story. So you can go online, NASA provides tools for predicting spacecraft orbits. So what I did is I just created a pretend imaginary spacecraft. I set it into orbit at 300 kilometres altitude. I chose a period of time that I knew there was a bit of activity on the storm front. This is 2003. And I just let this spacecraft orbit for a while. So this is about a month of time. Spacecraft initially at 300 kilometres, its altitude drops over time and eventually it comes down and re-enters the atmosphere. you can actually see it a little bit more clearly if instead of plotting the height that the spacecraft's at, you plot how many kilometres height does it lose per day. Starting off, it didn't lose very much, but as it gets lower and lower and lower, it loses more and more height, and eventually, as it gets down here, it's losing height really rapidly. This plot is showing the mass density, that kilograms per cubic metre, or pounds per cubic foot, if you like, of atmosphere for that same period. These two curves look identical, pretty much. So the rate of decay of the orbit is determined by the mass density. The mass density is determined by the weather. These bumps here, these little wiggles, are caused by storms. It doesn't look like much, but when you add up their effect, it means it changes when the spacecraft re-enters by days, many days. So how hard is it? You know, you've got a big spacecraft up there. There's been, not in the last couple of years, but 4 or 5 years ago, there were a couple of really big ones that re-entered. Ones where there were pieces of the spacecraft that could come down and impact a city or an orphanage or something, you know, that you don't want to hit. So you'd like to be able to warn people, if this thing is going to come down, you know, is it going to come down on top of you? The answer is we just can't tell. We can't tell where these things are going to come down. This is a prediction by the Aerospace Corporation, the best in the business for predicting where these re-entries will occur. This particular one, I think, was an upper stage of a Soviet rocket or something. They were on the 14th of July, 2003, they were predicting that this rocket stage would re-enter the atmosphere on the 17th of July, 3 days later. But how big was the uncertainty in when it would re-enter? It was 21 hours. Now, it takes 90 minutes to do one orbit of the Earth, and the spacecraft, you can see how these are successive orbits. So, you know, a 21-hour uncertainty, plus or minus, that's 21 hours this way, 21 hours that way, so it's really a window of 42 hours long. That means the whole Earth. You know, they can't localise it anywhere, even 3 days ahead. So, you know, good luck getting out of the way because you're not going to get any warning. So re-entry is difficult. Again, this is a busy slide, but I will say something about this one. The other part of the story is if you're a spacecraft operator today and your spacecraft is in what's called low Earth orbit, you know, 400, 500, 600 kilometres, roughly once a day you have to worry about, you'll get a notification saying there's a piece of space debris, there's a hatch cover, a battery, a fuel tank, you know, a rocket stage that's going to come close to your spacecraft, and you need to think about whether you need to do a little manoeuvre to avoid the chance that you might hit it. This happens all the time. In 2007, the operators of the Iridium spacecraft constellation, the satellite phone system, 400 times a week they had to at least think about whether there was a hazard to one of their spacecraft. 400 times a week. And the thing that really brought this into focus happened in 2009 when 2 full-size spacecraft collided in orbit. One was one of these Iridium spacecraft. It was still operating. It was being used to route phone calls at the time, you know, and it ran into a disused Soviet surveillance spacecraft. 42,000 kilometre an hour collision, happened at 789 kilometres and happened over Siberia. The fact that they collided is not the issue. What was the issue was that they knew in advance that these two things were going to come close, and they looked at it and they said, oh, we're okay, they're going to miss, we don't need to do any sort of correction. And they were wrong. and the satellites collided. So in the days before this, there was a forecast that said they might get as close as 117 metres. That's pretty uncomfortable. I wouldn't want to be an astronaut on one of these if that was all you had. But and in the subsequent days, they said, oh no, it's looking better, and yeah, we're going to miss by a kilometre, a bit more. We should be okay. But they were wrong, and the spacecraft actually collided. I'll show you a video in a second. Why were they wrong? They were wrong because they couldn't predict the effects of space weather that were changing the orbits too dynamically to know. Now this matters because now what it means is if you've got an error of a few hundred metres, or if you're only sure that you're going to miss by a few hundred metres, you better put a bit more distance between you and the hazard. And you actually have to put a lot, because if you only do a little correction, you don't know, you might actually have made it worse. You know, you actually have to do a large correction to be absolutely sure that you're not going to collide. And that costs fuel, and that's expensive for the operators. So this is a simulation. It's a company called Analytical Graphics. They do a lot of orbital prediction stuff. When everyone knew that the collision occurred, they said, oh, I better go back and have a look at this. And so they simulated it to see what actually happened. And this is what they came. This is more of a PR thing, but this is what they came up with. So this is the Iridium spacecraft. It collides with this Cosmos Soviet satellite, roughly 90 degrees to each other. They collided, produced two clouds of debris that were tracked, large numbers of trackable objects, and then a whole cloud of things that are too small to track. Those debris clouds went on and circled the Earth. You'll see in a minute. It looks fairly bad at the moment. It looks like, oh, they got these nasty clouds of debris, and they are. But in a second, this video will show you all the other stuff that NORAD and others are tracking. You'll see, well, it's an addition, but look at all the other stuff that's up there, you know. So this is a problem because, as I said, these close encounters with debris are so frequent now. There's a scenario called the Kessler syndrome where a collision like this could occur. It would produce some debris that would cause hit another spacecraft, cause more debris, and you can get a chain reaction. We're not quite at the point where that chain reaction will take off, but we're getting close. So space debris and tracking it is a big issue for spacecraft operators. All right, I'm getting a long way on my time here, so I'll try and speed up a little bit. How do we track these storms? We have instruments on the ground. This is our instrument at Toolik Lake. It's a photograph of the instrument. We have 4 of these across Alaska and a couple in Antarctica and various other instruments that support them. This is a photograph of, this is the hut that the instrument is in at Toolik Lake. This is another instrument that's currently at Eagle in Alaska. This is Greg, our machine shop supervisor, building an instrument to go to McMurdo in Antarctica. And the instruments look at the sky through a fisheye lens. So this is this little lens on the top there is how they look up at the sky. I just very quickly say the instruments measure the brightness of the aurora. That's this green band. They measure the temperature, which are these blue through red colours, and you can see the temperature changes near the aurora. And they measure the wind, which are these yellow arrows here. I don't have time to explain this in more detail. A single instrument gives you a reasonable look at the winds. You do much better if you have several of them together. And we actually have 4 of these in Alaska now, one at Kaktovik, one at Toolik Lake, one at Poker Flat, and one at Eagle. And by having them work together, we can get a much better view of the aurora. I can't say much about this except this is a status display that we have out at the rocket range that takes our wind data, it takes our camera data, it takes radar data, it takes magnetometer data and spacecraft data and brings it all together and provides us with a sort of a situational awareness nowcast display that we use to decide whether conditions are what we want for launching rockets. I will play this movie. This is bringing the winds, which are measured in white, you've seen before, the yellow arrows, the ion motion, and a whole bunch of other stuff together. I'll just play this movie and try and say a little bit about it as it's playing. There's spacecraft images. As the spacecraft move over, they're drawing in swaths of what they're seeing. Ground-based all-sky cameras, ion motion here from the radars, and you can see the winds that are being pushed around by the ions here. So we can bring all this together. There's a bunch of other stuff that we measure, vertical winds and properties of the wind field. We can bring all this together and produce a really nice view of what's happening weather-wise across Alaska. I'll let this play for just a couple more minutes. Here's the Aurora. This is Aurora south of Fairbanks. This is obviously an active night. Look how active the Aurora is. See, the Aurora became active, and you can see the wind changing in response to that. This is, again, showing you that the Aurora, when the Aurora is active, it affects the winds. I think I can probably jump ahead now if I do something like this. So I've got just a couple of minutes here. I want to finish off by saying, I said the last thing I wanted to say was, what can we do about this? Well, the answer is nothing in the sense that we can't stop the storms from happening, but what we can do is we can do a better job of predicting when they're going to happen and what they will do. And how do we do that? Well, the Naval Research Laboratory in Washington, D.C. accumulates observations from everybody who's got them, any data that they've got, and they put it into a big computer model, which is essentially a summary of all the weather that's been seen, and they use that to predict what the wind will look like. These are some predictions of the wind that are produced by that model. That's not the point here. The point is, what data go into it? Well, this blue horseshoe here and here are all our measurements from Alaska. Well, no, they're not all. They're our measurements from Alaska that we gave to the Naval Research Labs. And I'm very proud of the fact that We gave them a bunch of data to put into this model. It turned out we had so much data that they could only use 2.5% of what we gave them. They had to throw all the rest away because if they put all our data in, it would have overwhelmed everything else. So all these other points here are from other, they're from spacecraft and other institutions, other measurements. But here in Alaska, as I said, this is our contribution, the blue stuff. This is an operational model. This is what the forecasters use to tell them how their spacecraft are going to behave. This is our data from Alaska going into it. And as I said, by far, we are the biggest contributor of data to that model. I'll just finish by saying, these storms, I've sort of talked about how they look to us here in Alaska. They're driven by the Aurora. The Aurora is occurring over Alaska. But those air parcels, they don't just stay over Alaska. They cover the whole globe. Really, we've got nice instruments here, but really you'd like to know what's happening all across here and further on down over the lower 48 of the US where there's, so much of the population is. So our community is talking about trying to take what we have here in Alaska and multiply it many times over. These instruments only work at night. You can only see the Aurora at night, you can only see the dim light at night, so you don't get any information during the day. But then as the nighttime passes through, what's shown here is imagine having instruments like the ones I've been showing you all across Canada and down over the main part of the US here. What would you see? So they've taken a computer model of a storm and imagined what we would see if we were observing it during the storm. You can see how complicated this wind flow is. There's all sorts of stuff going on, lots and lots of flow here. So our community is working now on ideas for how we could fund and build something like this, which would let us see, really what the story looks like for the whole US and not just for Alaska. So with that, I will give you a summary and stop. So let's see, the main points I want to take away from this are, there's this region we call the thermosphere. It's the outer layer of our atmosphere, 100 kilometres and up. It's tenuous. It doesn't act all that much like the air in the room here, but it does still experience weather. Not a very familiar form of weather, but it experiences weather. The weather is driven by eruptive emissions from the sun, and that frequently produces these large storms. There's lots of other effects of the storms I haven't even touched on. I've just talked about how the sun upsets the top layer of our atmosphere. The effects on the atmosphere affect lots and lots of technological aspects of our society, but very particularly they affect spacecraft orbits, whether the spacecraft are going to have encounters with debris, re-entry, those sorts of things. Geophysical Institute has an active program to monitor and understand the storms, using both the ground-based instruments I've spoken about here and also sounding rockets, which I haven't spoken about. And our near-term goal is to expand the monitoring network to include sites in Canada and the lower 48 of the US. So I'll leave you with that and take questions.